Let's come to our huge topic, which is review of all units. Final course review it's called. The objectives of this topic is to discuss, introduce the concept in automated theory and the theory of computation, identify different formal language clauses and their relationships, design grammars and the recognizes for different formal languages, prove or disprove theorems in automated theory using its properties, determine the feasibility and interactability of computation problems. The main topic which we are discussing here is in the TOC is regular language, contextual languages, Turing machines, and the computability. So I'm saying hierarchic form. The language hierarchic form, which is the lowest power of language, is called a regular language, which is recognized by deterministic finite automata. Next to superior highest language is called a contextual language, which is again accepted by push-down automata. The next level hierarchy higher language is called a context-sensitive language, which is accepted by linear bounded automata. The next level is called recursive language. Turing machine always fault for this recursive enumerable language. Turing machine that need not always fault. If it is acceptable, the Turing machine halt. Otherwise, not acceptable. So it is a undecidable problem. The Turing recursive enumerable language is called undecidable problem. So non-recursive enumerable language, no Turing machine exists. Non-recursive enumerable languages, no Turing machine exists for accepting language. Interplay between the different computing components. You implementer, designer, user. Implementer user is called problem, languages, what problem, what is the language you're using. Designer, so expressions, grammars, what like grammar rules and regulations for this you are going to use called design. Implementers, machines, hardware, software, what is the language, hardware, low level implementation. This is called interact between different computing components. You should know that. Regular language topic, smallest, simplest form of all the languages called, which is called finite automata. It's called non-deterministic finite automata, deterministic finite automata, epsilon within non-deterministic finite automata, a regular expression, regular language and properties, closure properties, minimization. These are the topics in the regular language topics. Finite automata. Let us see the finite automata. Deterministic finite automata, the machine can exist only one state to at any one state at a given time. Non-deterministic finite automata means the same input we can exist, we can transmit to more than one state. It's called non-deterministic finite automata. Epsilon with non-deterministic finite automata is an NFA that allows epsilon transition. Empty transition can be allowed one state to another state with empty movement, which is called epsilon transition. So what are the other differences? Conversion methods are there. Deterministic finite automata DAP with the 5 tables. Is a Q is a set of states, summation is a set of inputs, Q is a starting state, F is a final state, delta is a transition. So these are the things, the state diagram, state run. We can represent in DAP in 2 methods. One is called diagram method, which is called state diagram method. Another is called table. This is called state transition table. Okay, DAP construction checklist. It states the finalists, how many finalist states are there, what is the input, what is the starting state, what is the final state, how many inputs are given, how many number of states. These are all should be listened before going to construct a finite automata. Non-deterministic finite automata also same like the deterministic finite automata, 5 tables. This also having state diagram, trend table. So here also having set of states, set of inputs, starting state, final state, transition. Transition means one state to another state. Here the non-deterministic finite automata can transmit, able to transmit n number of statements, 2 power n states can be transmitted for the single input. So NFA to DFA can be checklist for the NFA to DFA. 2 approaches enumerate all the possible subsets is one method. So use lazy construction strategy to save the time to introduce subset state only for as needed. So any subset containing the accepting state is also the accepting state of the DFA. So have you made a special entry for the phi for the empty subset? This will be correspond to the dead state. Epsilon NFA to DFA conversion. Checklist for this. First, take the closest states of the state. New state was a new clauses are coming in. That new clauses we can combine. Remember, enclose Q into the Q list. Same 2 approaches NFA to DFA. Enumerate all the possible subsets. So use the lazy construction strategy. So only difference the epsilon closer is the before, the after transition. The subset pi correspond to a dead state. Regular expression is a way to express accepting patterns, operations of the regular expressions. This is a within bracket is a regular expression. A language contains a two addition from the two non-terminals for regular expression. Language will be followed by this also be one followed by another also regular expression. One followed by closer also regular expression. The language, the regular expression checklist capture all the cases of valid input strings. Express each case by a regular expression. Combine all them using the plus operator by attention to operator precedence. Regular expression, DFA to regular expression. Enumerate all the paths from start state to final state. Regular expression. Generate regular expression for the each segment under concatenate. Combine the regular expression for all the each in each path using the plus operator. Regular expression to epsilon NFI conversion. Inside to outside construction, start making states to every automatic unit for the regular expression. So combine using concatenation plus and star as an automate for this, all the things. For connecting adjacent parts using epsilon jumps, remember to note down final state, pumping lemma. So it is used to prove the given language is regular or not. These are the checklists for the pumping lemma. Left n is a pumping lemma constant. There is a construction of the W is a word which contains more number of lines are there. Now W can be divided subdivided into three parts which will be satisfied in pumping lemma language. So check all the three conditions. Use one of these two strategies to arrive at the contradiction for the same some other string constructed from the W. Pumping lemma should have a k value should be greater than equal to 2. Pumping lemma down to k equal to 0. So regular language properties, closed under union, closed under interaction, closed in complementation, closeness and difference, closed and reversal. Homomorphism and inverse homomorphism also possible in the regular language properties. Look at all the DFA and NFA construction for the above DFA minimization. So remove the unreachable states first. Deduct equivalent states. Table filling algorithm. So wherever the equivalent is there, that means you have to fill this. Then mark X. So then mark X where the distinction between the using one symbol transition. Also mark equivalent whenever the states are equivalent. First to distinguish using the already distinguished states one symbol. Repeat those two symbols. Repeat for the such two symbols. So on the state left distinguished. Terminate all when the entries have been filled. Finally, modify the state diagram to keep one representative state for the every equivalent classes. Other properties, there are two DFA equivalents application of the table filling algorithm also. So CFL, context-free language topics, context-free grammar, push-down automata, context-free languages and pumping lemma, context-free grammar simplification oral forms, context-free language properties. Context language G equal to VTPS, where V is a variable, T is a terminal, P is a properties, is the starting state. So we can also possible leftmost, rightmost reverse, and equivalence also. Regular language versus context language, right linear. So context language, design the context language. So many techniques are using for the design context language. Make your own start symbol for the combining this grammars. So S implies S1, S2, S implies S1 and S2. Such symbols. A implies A, S, replicating the structure side by side, but S implies A, S, B, S. So like this, we can design our own. So conversely, the proof of the correctness, use the induction on the string length. Ambiguity of the context from one string more than one parse tree is if one string more than one parse tree, that grammar is called as ambiguous grammar. Finding one example is sufficient. Converting ambiguous grammar to non-ambiguous grammar not always possible. If possible, the ambiguity resolving techniques. Ambiguity of the context of language. It is not possible to build even a single unambiguous grammar. There can be only one stack top symbol that can be many symbols for the replacement. PDA equal to epsilon NFA plus a stack. PDA plus epsilon NFA plus stack is called in epsilon PDA equal to epsilon NFA plus a stack symbol is called as a pushdown automata. So P is equal to definition for the pushdown automata. Okay, transition, current state, current input, tab stop, current next state, next replacement input, instantaneous description. So what is the current state? What is where the pointer is available? what is the input, what is the replacement. The state diagram is a diagram of PAPM. So the PDA is a current state, is a next state, which is A is the next input symbol, X is the current stack symbol, Y is a replacement symbol. Where the direction is direction. This time in the PDA techniques, there are two types of PDA, accepting empty stack, accepting final state. So converting one from another, assigning state for specific properties, pushing and popping stack symbols for matching, converting CFJ to PDA, introducing new stack symbols may help take advantage of non-deterministic. CFG simplification, eliminate for the epsilon productions. So you can eliminate for epsilon, eliminate for unit productions, eliminate for user symbols. You can eliminate all the things, you can simplify the grammar. Chomsky normal form, produce the form of this A implies PC, A implies CA. The grammar does not contain user symbol, unit production, unit, user symbol, unit, and epsilon production. So converting context-free grammar to CNF form. Introduce new variables that collectively represent a sequence of other variables and terminals. New variables for each terminal. In a Chomsky normal form is a positive size. The length of the longest part of the positive is n, then length of the W is equal to 2 power n minus 1. Pumping lemma for contextual language. So there exists a constant n, the statement. If z is any string in the language statement, z length is greater than or equal to n, then we can rewrite z equal to pi subcontinent u v w x y. The subject to the following conditions: u v w x length less than or equal to n, vx not equal to empty for all k greater than equal to 0. So u v for k, w x for k, y is in the language. If it is available in this, we call it a contextual language. Otherwise, if you get a counteraction, you can call this language is not contextual language. Using pumping lemma for this, let n be the pumping lemma for the language constant. Pick one word z language statement. So u will be divided into five subtopics. First, argue the because of the conditions 1 and 2. The portions are covered by UVWX. The main string WZ will have the satisfy more property. The next, argue the pumping lemma up or down. You will get a new string from the Z that is not in L. Closure properties of pumping contextual language. Closure properties are you can close under union, concatenation, Riemann closure operator, substitution, homomorphism, inverse homomorphism. Context-based languages are not closed under intersection, difference, and complementation. Closure properties for the watch out for the custom defined operators, prefix L or LNTM. This is also concatenation for use a defined operation, custom defined symbols. Other than the standard symbol 0, 1, ABC, I as example as C as a custom defined closure property symbol. The basic Turing machine, all of you know that the Turing machine is a finite control here. There are 7 tuples are there, which is called a set of states, a set of inputs, a set of stack symbols, a transition symbol. Starting state of the Turing machine is a blank symbol.